Hi, thanks for joining me. Today I'm going to be going over problem 1 from week 6 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. Anyway, this is the problem I'm going to be tackling today, and it involves infinite series and Fibonacci numbers. So we have f0 being equal to 0, f1 being equal to 1, and fn plus 1 equals fn plus fn minus 1. So this recurrence relation, and this probably seems familiar, it's just the sequence of Fibonacci numbers. We want to find the unique set of real numbers a, b, c and d, with b being a positive integer, so a natural number, such that this guy here holds true. That is the sum from n equals 0 to infinity of f of 2n all squared minus a times fbn plus c, that guy there, that infinite series there, equals d. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so I've written up a fact about the Fibonacci numbers up here, and that is that the nth Fibonacci number is given by this formula here. So 1 over root 5 multiplied by the thing in square brackets, and that is 1 plus root 5 over 2 raised to the n minus 1 minus root 5 over 2 raised to the n. Now, I'm not going to be proving this fact in this video. It's a pretty common fact about Fibonacci numbers. There are, I guess, at least a couple of ways you can prove it. One is just by proving it by induction from this guy here, or the other way is kind of using the definition of the recurrence relation of the Fibonacci numbers and kind of putting that into matrix form, a 2x2 matrix form, and then from that finding the nth one by diagonalizing the matrix. But yeah, I'm not going to be proving this in this video. We're just going to use it as the truth. And of course, this is what we want to do, find a, b, c, d real numbers with this equation here holding true, the infinite sum of f2n squared minus a fbn plus c equals d. The first thing we want to do is notice that we've got an infinite series and it converges to d. So that must tell us that the thing we're adding up, this guy here, this guy must tend to 0 as n tends to infinity. Because if it didn't tend to 0, then there's no way this sum here could converge, let alone converge to d. So certainly we must have the thing inside, the summed, that guy must tend to 0. So we have that the limit, as n goes to infinity, of f2n squared minus a times fbn plus c, this guy here must equal 0. But I can just kind of bring this c onto this side, so I get the limit of now f2n squared minus a fbn is just equal to minus c, like so. But now what we can do is have a look at this side here and notice that we're taking n to infinity, so we can kind of use our formula for fn. And I guess one thing I should mention is this 1 minus root 5 over 2 term, that is going to be a negative number which is bigger than minus 1. So this term here, the thing inside the brackets, is some real number between minus 1 and 0. And why that's important is because as we take n to infinity, this term here is going to tend to 0. So in some ways we can kind of ignore it because we're looking at n going to infinity. So firstly, f2n squared. Well, just using our formula, we know that f2n is approximately 1 over root 5 times just this guy here. Because we know we're looking at large n, so we can kind of just ignore this 1 minus root 5 over 2 to the n term, because that's going to tend to 0. So we simply have 1 over root 5 times 1 plus root 5 over 2. But instead of to the n now, we have 2n, because we have 2n here. And yeah, I guess we can also ignore the 1 minus root 5 over 2 to the 2n, because of course that's still going to tend to 0 as n goes to infinity. So we have f2n is approximately this guy here. So if I square it, then I square this right hand side, so I get 1 over root 5, well that turns into 1 over 5. And this guy here is just going to turn into a 4n, like so. So f2n squared is pretty much this guy here for large n, plus some very small term which tends to 0 as n tends to infinity. And then what about a times fbn? So a times fbn, well, let's just plug it into this thing here, and again we can ignore this second term because it's going to tend to 0 as n tends to infinity. So this is approximately a over root 5 times 1 plus root 5 over 2 to the 4n. Sorry, to the bn. I'm jumping ahead steps, as we'll see in just a second. So we have a times fbn is approximately this guy here. But what we want is we're looking at the difference of these two things here, and we want that to kind of go to 0. And first you notice that b must be equal to 4. Because if b is not equal to 4, if b was, say, I don't know, 3, say, then we have this guy here is an exponential which is bigger. You know, 4n is going to be bigger than 3n. So as we take n to infinity, when we do this guy minus this guy here is going to dominate. And thus this difference will tend to positive infinity. Okay, and if, say, this was a bigger number than 4, say 5, then when we do this minus this, it's going to tend to negative infinity. But of course, we don't want it to tend to negative infinity. We want it to converge to a real number, namely minus c. Hence, we must have these exponents here are the same. So that tells us that b must be 4. So b equals 4, like so. And also, obviously, if a does not equal 1 over root 5, then these kind of leading coefficients here won't be the same. So these guys won't cancel out with one another. So say a was not 1 over root 5, say this thing here was 2 over root 5, like so, then this whole thing here would just be 2 over 5. And when we did this minus this, we just get minus 1 over 5 times 1 plus root 5 over 2 to the 4n. And obviously this guy here is going to convert, diverge off to negative infinity, because this thing here turns to infinity and this thing here is non-zero and negative, so it's going to tend to negative infinity. So we need this number here to be 0 for this guy here to tend to 0. So we must have, if we go back to what we had before, we had a over root 5. So when we look at the difference of these two things, for them to be equal, when we do this minus this, for that to be equal to 0, we must have that a equals 1 over root 5. So that this guy here just equals a fifth. So we have that a equals 1 over root 5, like so. Okay, so what we've done so far is we know we want to find a, b, c, d satisfying this guy here. So we've applied some necessary conditions. So the first necessary condition was this limit here had to hold. And then we use the fact that, as n tends to infinity, this guy here vanishes. And then we notice that this thing minus this thing had to converge to some real number, namely minus c, and hence couldn't diverge off to positive or negative infinity. And that gave us the value of a as well. So now, from our necessary conditions, we've already derived the value of a and b. Let me clean up the whiteboard and we'll work out what c and d have to be as well. Okay, so now that we've worked out the values of a and b, to work out c is actually quite straightforward using this guy here. C, of course, is just minus this limit here, so minus the limit as n goes to infinity of f2n squared minus a times fbn. But a and b we've worked out, a is 1 over root 5 and b is 4. So if we just have a look at this thing here, and I've written that here, so that's just f2n squared minus 1 over root 5 times f of 4n, then we can just use our formula for fn and just plug it in, and I've skipped out the middle steps, but this all in all equals minus 2 fifths plus 2 over 5 times 1 minus root 5 over 2 to the 4n. And of course, this guy here, or if we take the limit as n goes to infinity of this thing here, so limit as n goes to infinity of this thing here, we should be getting minus c. But remember, 1 minus root 5 over 2 is some real number between 0 or minus 1 and 0. So that means as you take n, as you raise it to n and take that to infinity, you're going to get 0. So this thing here is going to vanish as we take the limit. So we simply get that minus c is minus 2 fifths. So of course that tells us that c is just 2 fifths. And now we have what c is as well. The last step now is to compute what d is. Okay, so the last thing we have to do is compute d, and in fact I've written out the value of d here. It's 5 plus 3 root 5 divided by 25, and the reason I've written it down there is just so I don't forget what it is. Anyway, we have f2n squared minus af times bn, or af of bn, sorry, plus c equals this guy here, 2 over 5 times 1 minus root 5 over 2 raised to the 4n. Now this essentially just comes directly from this definition here, and the values of a, b, and c that we have. But remember, just on the whiteboard before, I skipped out the middle steps, but I showed that this guy here is just equal to 2 over root 5 times 1 minus root 5 over 2 raised to the 4n minus 2 fifths. So if I just add the 2 fifths to both sides, which of course is just c, I get this equation here. Anyway, we want to take the sum as n goes to infinity of this guy here. So obviously it's going to be the same as the sum as n goes to infinity of that guy here. So the thing we want to work out, this guy here, let's call it s. So s is equal to this 2 over 5 times the sum as n goes from 0 to infinity of this thing here. So 1 minus root 5 over 2 raised to the 4n. But of course this thing here is just a geometric series, and perhaps an easier way to see that is if I write this as to the 4 and then do this to the n, like so. And our first term, when n is 0, this thing here is just 1. Then we get 1 minus root 5 over 2 raised to the 4, then 1 minus root 5 over 2 raised to the 8, and so on. But we can just use our formula for a geometric series, and this thing here is simply 2 over 5 times 1 over 1 minus r, where r is our common ratio, and our common ratio is just 1 minus root 5 over 2 raised to the 4. So that's 1 over 1 minus root 5 over 2 raised to the 4. And that is our value of d, because we know s equals d. So this thing here equals d, and yeah, if you go ahead and expand out 1 minus root 5 over 2 to the 4, and then, collect like terms, simplify it and whatnot, bring this 2 over 5 into the mix, you're going to end up, if you do everything correctly, with d equals 5 plus 3 root 5 over 25, and that's our value of d. I hope that has all made sense, and I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.